Hi everybody. Today we're going to be doing a developer's introduction to Hedera Hashgraph and the Hedera Consensus Service. My name is Brady Gentile. I'm a product marketing manager at Hedera Hashgraph. I'm going to be doing the first part of this developer workshop, and then Cooper Coons, developer evangelist at Hedera Hashgraph, is going to be taken over for the second part. So let's take a quick look at the workshop agenda for the day. We've got part one, which is the overview. So I'm going to be explaining how Hashgraph consensus works and the differences between Hashgraph and blockchain. Then we're going to talk about the Hedera network services and the fully decentralized governance of the Hedera network. Then Cooper Coons is going to take over. He's going to be doing a coding walkthrough with you. That'll include installation, setting up your environment, and then submitting your first message and creating a topic for Hedera Consensus Service. All right, so to kick things off, let's talk about the enterprise adoption of public distributed ledgers. There's some fundamental obstacles in the category of public distributed ledger technologies, which need to be solved before they achieve mainstream adoption. And the requirements that we've identified at Hedera include performance. So you need to be able to transact quickly with certainty, and the network needs to support applications that are running at web scale. Next, there's security. So you have to be able to trust the network is going to be DDoS and Sybil attack resistant. There's stability. The platform needs to be stable, so you need to, one of the big important things is preventing forks of the network. It's an incredibly important aspect of security because application developers don't necessarily want to have to split their application state and manage multiple currencies or applications running across, forked networks. And then finally, there's governance, so a fully decentralized governing body for code changes and decision making is a critical aspect for the integrity of the network. So in this brief overview, we're going to touch on all four of these different aspects. So let's start with blockchain versus Hashgraph and try to understand some of the differences here. The most ubiquitous public blockchain technologies today, so Bitcoin or Ethereum, they utilize what's known as proof of work consensus. And there's some downsides to proof of work consensus in order to achieve an adequate level of security. And the downsides include things like, it's computationally heavy and consumes a lot of electricity. The consensus of transactions, they aren't final but probabilistic. So each block that's added to the chain only makes it more likely that a transaction in a previous block is true. It doesn't actually confirm that those transactions are final and are good to go. And also the proof of work blockchain is difficult to scale with regards to throughput. If we switch over to Hashgraph is both a consensus algorithm and a data structure. It can be defined as a direct acyclic graph, or DAG. It achieves a similar end result as blockchain, which is decentralized trust, but it does it in a way that's more efficient. So it's faster. You can get, at least right now, up to 10,000 transactions per second. It's more fair. The transactions on Hashgraph are fairly ordered. You can't bribe nodes on the network to put certain transactions ahead of others. And it's secure. It achieves the property that's known as asynchronous Byzantine fault tolerance, which is considered the highest grade of security for a public distributed ledger. So it's incredibly lightweight, and it requires far less electricity to use Hashgraph than proof of work blockchain. So how does Hashgraph consensus work? To give you a quick history, the Hashgraph consensus algorithm was created by Dr. Lehman Baird. He's the co-founder and chief scientist of Hedera Hashgraph, and he began working on distributed consensus at scale a little bit before 2012 and completed the conceptual architecture in 2014. Then the Hashgraph white paper was published in 2015, And since then, there's been COQ proofs that have validated that the Hashgraph algorithm is in fact asynchronous, Byzantine fault tolerant, which ensures, again, the highest degree of security for a public distributed ledger. So let's learn a little bit about how Hashgraph works. And to understand Hashgraph, you'll need to understand gossip about gossip and virtual voting. And so we have a set of 8 computers here on a Hedera network, and it's labeled Alice through Hank. And Alice, in this scenario, has a transaction that she wants to send out. And so she puts the transaction inside of a message, and that message is sent using a gossip protocol. So in this transaction, she sends it to a random person. In this case, it's Dave. And then Dave takes that message and sends it to a random person. And then, Alice sends the same message to Gina, and then they send it to a random person. And exponentially fast, it expands outwards until the whole world is aware of the transaction. And so now, what if Bob and Carol, they've got transactions that they want to send? Well, they put them inside of messages, which can be sent out to random people as well, and the cycle starts over. There's 2 and then 4 and then 8, and it continues to grow exponentially until the whole world is aware of these messages. But how do we know what time each message received reached the world as a whole? So we could keep track of when each person received each message, and that's what Hashgraph does. You can see that the messages and timestamps for each person are on the left there. And we take all of those timestamps when each node received each message, and we sort them. So all the times for the red message and the blue message and the green message are sorted there on the left side. And from there, we're going to take the median timestamp, the middle of the list. And this tells you when each of the 3 messages reached most of the world. And, this taking the median instead of the average, this accounts for abnormalities. If for whatever reason some node is an outlier, you're still going to get the middle of the group by doing median. And if we sort the messages by that, then that puts them into a fair order. So you see we've got Alice's transaction, Carol's transaction, and Bob's transaction all ordered based on the median timestamp of the entire world. And with this gossip protocol, if we wanted to know when each person received each message, you'd think we'd have to send receipts around in order to determine that. But with Hashgraph, you actually don't need to be sending receipts around. That would be incredibly bandwidth inefficient. And so what Hashgraph does instead is within each of these messages that are sent around, these messages include a transaction. So whatever you want to create, such as a cryptocurrency transfer, could be the transaction. It has a timestamp of when you're claiming that you created it. It has your digital signature, and it includes 2 hashes. There's a cryptographic hash of the last message you made, and then the last message that you received. And by just including these last 2 hashes, it ties all of them together. And so we can store the graph in memory across every computer. You can see there's graphs associated with Alice, Bob, Carol, Dave, etc. all across the bottom. And it's a complete history of how they've talked to each other. So they're not just gossiping the transactions, they're actually gossiping about the gossip. So they're talking about how they've been talking. And once we have this hash graph in memory across each of these computers, we can look at it, and then we can do what's called virtual voting. So we can look at the timestamp and know when each person received each message. We don't have to talk to each other about it. We don't have to send out additional messages when you receive things or what order to put them in. All of that is included without any additional overhead. And this is what allows Hashgraph to achieve consensus so efficiently. So what is the lightweight and efficiency of Hashgraph? How does that translate into real world usage? And so what Hedera Hashgraph achieves today is around 10,000 transactions per second. That's all on a single shard and on ledger. And this is for HBAR cryptocurrency transfers, and we'll learn a little bit more about this later, but Hedera consensus service transactions, and right now it can scale up to 10,000 transactions per second. Each of those transactions costs a mere 0.0001 cents, and each transaction achieves finality, not probabilistic consensus, in 3 to 5 seconds. So let's take a look at the network services that are available to application developers building on Hedera. So the first service that we have is the Hedera Cryptocurrency service, and this service lets you create accounts on the network and transfer native HBAR cryptocurrency, which is the Hedera cryptocurrency. HBAR has two purposes. So it's used by developers as fuel to pay for API calls on the network and powering their applications. And it's also used as a network security mechanism. So the Hedera network is a proof of stake network, and HBAR is staked to nodes, and that adds weight when they are voting on transactions in order to achieve consensus. The second service is the smart contract service. Smart contracts can be written in Solidity. They're executed based on the order they're received, not on the amount of gas paid. So unlike Ethereum, there's no bribing of nodes. If you're familiar with that concept, transactions are just executed as soon as they're received. You can also transparently define administrative keys for a contract. And so this allows the owner of the contract to make any necessary changes to what would otherwise be an immutable contract. Or you can set it up not to do that. It just depends on how you'd like your implementation to go. So at this time, it's actually recommended to use the Hedera consensus service, which we'll get to in just a minute, in place of smart contracts for a large number of use cases. And this is because today we're still limited on performance and scalability when using smart contracts on Hedera, and that's even with Hashgraph consensus, we're still limited. We're still limited on that front. The third service is the file service, and that allows for claims and revocations for identity use cases. You can also anchor files that are stored in an external repository by creating a hash that's on ledger. The file service utilizes Hashgraph consensus to ensure that the file is distributed across every network node and that it's always available. So finally, we have the Hedera consensus service, and last year Hedera teamed up with Brian Gross. He's a product manager at IBM, to create a white paper detailing this new service that was released this year. This allows developers to fully realize the speed, security, fairness, and trust of Hashgraph consensus in both new or existing applications. It's very exciting. And so with Hashgraph Hedera consensus service, it lets you build applications that are as fast as Hashgraph consensus because it takes advantage of the native speeds of the algorithm. It allows for an incredibly high throughput of transactions to be sent to the network at the same price of a cryptocurrency transaction. So that's 0.0001 cents. It also guarantees the order of transactions to be fair. Using the Hedera consensus service, you can incorporate decentralized trust at scale into existing applications like the Coupon Bureau. The Coupon Bureau, they keep track of manufacturer coupon redemptions at retail outlets like Target and convenience stores and other places that are similar to that. The problem that they ran into is that their data that's collected can be fragmented, non-standardized, and sometimes fraudulent. Additionally, the process is not near real time, which adds to the ability for things to be fraudulent. The solution is by using Hedera and specifically the Hedera Consensus Service to bring standardization and efficiencies to the marketplace with transparency and trust in near real time. So by writing the redemptions onto a public ledger in a standardized format, we're allowing for third-party validation and auditing for any stakeholders, whether that's the manufacturer, the retail outlet, the individual who redeemed the coupon, or any person that needs to do auditing and trust that the information is accurate. The industry will be able to have even more confidence and trust when using Hedera Consensus Service for this specific use case. Another platform that's being used for Hedera Consensus Service is AdStacks. They're a digital advertising platform, and today the problems that are being faced for them are fraud and a significant amount of fees being distributed to intermediaries that are there to create trust between advertisers and publishers. In addition to that, there's just a general lack of transparency in the space as well. With Hedera Consensus Service, they're able to create a scalable and auditable trail of these payable advertising events. That includes timestamps for when those events occurred, and it happens in near real time. So data written to Hedera using Hedera Consensus Service that's used for fraud detection, fraud prevention, the reduction, and measurement as well. And an interesting fact with AdStacks is they actually started with the Stellar platform, but they weren't able to scale to the millions of events per day that they're pushing and continue to push. So finally, let's talk about fully decentralized governance before we dive into getting started with the SDKs and we hear from Cooper Coons, developer evangelist. So because Hedera is a public network, it needs to be governed in a decentralized way. And the model that was used for Hedera governance was actually chosen because it was based off of the Visa model. So the governing body of Hedera consists of up to 39 global organizations, and those organizations actually equally own part of the LLC. They're found across 18 different industries and 5 different continents. Each member is required to run a mainnet node, and members are not compensated beyond network node payments in HBAR cryptocurrency. It's decentralized across time as well, not just industry and geography. There's a 3-year maximum term with up to 2 consecutive terms. On the governing council today, it consists of these folks, people like Swisscom, IBM, Google, Nomura, it's a bank in Japan. Magalu is like an Amazon down in Brazil. A number of different industries and types of companies. They all share an equal part of the LLC. They're required to own and operate a node on the main net, and they meet quarterly to make decisions about the direction of the network. You can actually find the full LLC agreement on our website, including all of the quarterly meeting minutes for the council meetings at hedera.com/council. And so that's pretty much it. We've touched on the entire Hedera ecosystem here. It's a complete overview. We have the Hashgraph consensus that's underpinning the entire network. It's fast, fair, and efficient. You have all of the network services on top of that, the cryptocurrency, smart contract, file, and consensus service that developers can use in order to build their applications. You've got the code base for the Hashgraph platform and the network services governed by the Hedera Governing Council. And then you've got the different third-party applications that are running on top of it. And we talked about the Coupon Bureau and AdStacks. And today there's about 32 total applications running our mainnet, and we will have many more coming soon. So before we dive into the coding examples, I just wanted to share with you a link to the Hedera documentation and specifically the Hedera supported SDKs for Java, JavaScript, and Go. There's also a number of community supported SDKs in other various languages that you can check out. They're not maintained or officially supported by Hedera, but there's a really good community that's growing around the development of those. If you're interested, you can even build an SDK in a language that you want to use but currently isn't supported, and we know the community would be very appreciative of that. And with that, I'd like to pass things off to Cooper Coons. As a reminder, he's going to walk you through the installation process with the JavaScript SDK, setting up your environment, and then walking you through creating a topic and your first message using Hedera Consensus Service. If you like what you hear with Cooper and you learn something interesting and you want to keep going, we've got a ton of tutorials by Cooper on our YouTube channel. And at the link that we've got on the screen there, you can check those out, or you can just go searching on YouTube for Coding with Cooper. And with that, I'd like to pass it off to Cooper. Thanks.
Hi everyone. I'm going to teach you how to get started with Hedera's JavaScript SDK. I'm using Visual Studio Code, but please feel free to get set up in whatever environment you choose. The first thing I'm going to do is open a new terminal and run npm init. This is going to generate our new node project. You can fill in this initialization process with the default values, or you can pass it in things that are relevant to your project or the tutorial that we're doing right now. After this is finished, the next step is actually installing the Hedera Hashgraph JavaScript SDK. And you can do this by running npm i @hashgraph \SDK. And after that's finished running, we can go and check and make sure that this was installed properly by seeing that it was added to our list of dependencies and making sure that it was included in the node modules folder that we have locally. After that, we've successfully installed the Hedera Hashgraph JavaScript SDK. And that's it for your first tutorial. In part 2, we're going to teach you how to set up your environment and configure your Hedera client connection. The first thing you're going to want to do is run npm i.env. This is a package that will allow us to grab access to the environment variables we're going to set up in a second. After this, we're going to create a new .env file. We're going to open that file and add our desired key value format. This actually contains a key and our account ID. But maybe I should specify that this is our private key associated with that account ID. If you don't have an account for the Hedera testnet yet, you can sign up at portal.hedera.com and copy and paste the account ID and private key into the environment file that we just created. After that, we're going to create a new file for our Hedera client. I'm going to name mine hedera-client.js, but feel free to name it whatever makes sense. We're going to open that new file, and then we're going to require that our .env, our environment, is configured. And then after doing that, we're going to import the client module from the Hedera Hashgraph JavaScript SDK. And then the next thing I'm going to do is say I want a new constant, and I'm going to name this Hedera client to match the name of the file. And this is going to be a new client from the Hedera JavaScript SDK. Within here, we're going to define our network connection and pass in one or as many nodes as we would like to connect to, as well as the account ID of that node. So that way we can pay it some HBAR. The other things that we can pass in include the operator, which is the account ID and the private key that is going to generate, sign, and execute these transactions for us that we're going to use in all of our other tutorials. And this is going to be the process.env and then the specific key value format that you added before. And then the final step here is going to be exporting this constant variable as a JavaScript module so that we can use it in all of our other tutorials. And so after this, you should have your environment set up and you should have your Hedera client connection configured.
In this one, I'm going to show you how to get started with the new Hedera Consensus Service, which is a novel publish-subscribe architecture for blockchain applications or traditional applications. It can be integrated into whatever you're building. Let's get started. All right, as you can see, I'm in Visual Studio Code, and just like in our other tutorials, I have the Hashgraph SDK already installed at version 1.1.8. You might want to make sure that you're running the same version for this example. Going back to our index.js file, I'll start off by including all of the packages that we're going to use in this example. By requiring .env to be configured, that'll allow us to have access to our environment variables that we'll use in this example. After this, I'll include all of the modules from the Hedera Hashgraph JavaScript SDK that we're going to need. All right, well, that was quite a lot of modules, but I'll walk you through what each of these actually do when I use them in this code. So don't worry too much about them yet. Now that we've imported all the modules that we're going to need, let's write an asynchronous function that will build this example demo that we're going to use today. So within our main function, we're going to start using the Hedera Consensus Service to build this publish-subscribe architecture that we're looking for. There's a variety of moving parts here, so let's kind of take it one step at a time. The first thing that we should probably do is configure our client connection. That'll be this JavaScript module that we have here. So I'll start off by instantiating a client for the test network, and then using my account ID and private key to configure my client connection. Awesome. And you can see here that I have a client configured for the test network. You could, just as easily configure this for mainnet here if you were ready to deploy to the main network. But just for this example, I'll stay on the test network. The next thing that we're going to do is create a new consensus service topic. So a consensus service topic can be thought of as a private channel for messages. Or you can leave it open and allow anyone to write messages to that channel or topic. And so in this way, you can build really cool message queues, event streaming applications, and so many other fun things. And so all that I'm doing here is building a new consensus topic create transaction and executing it with my client that I just configured in the last step. That client will pay for all the fees and generate the transaction and all the nice things behind the scenes. After we ran this consensus topic create transaction, we'll need to get the receipt of that transaction, which should contain the new topic ID if the transaction was successful. And again, my client will be the one executing this and sending it to the test network. assuming that this transaction receipt was successfully generated, it will contain our topic ID. So let's grab that one now. Awesome. And this should be all the code that we need to be able to create a new topic with the Hedera consensus service. So I'm going to log this now just to see that we're all set up so far. And if I want to be able to run this example and test out our consensus topic create, I'll need to call that main asynchronous function that we just wrote. As you can see, I'm only using the client and the consensus topic create transaction modules so far. Once I've confirmed that this implementation is working, I will move on to using these other modules. So by opening a new terminal, we should be able to run node index.js, which should execute this script. And we will see whether or not we were, we were. So we now have a new topic on the test network at this address, 30316. So now we know that this block of code is all set up properly. We're able to build our client connection and create new topics on the consensus service. The next thing that we're going to want to do is create our publish code. So code that will publish new messages into this topic. And to do that, we'll use the consensus message submit transactions here. For this example, I'm just going to maybe send 10 messages to this consensus service topic just to show you how easy it is to push messages into this infrastructure. So we'll start off with a for loop. And so when we're building the consensus submit message transaction, there's a few specifications or parameters that we need to define. The most important of which is probably the topic ID. And so set topic ID, we're going to use the new topic ID that we just dynamically created. After defining which topic we would like to publish these messages to, we will specify the actual messages that we would like to send over the consensus service. And so we'll say hello HCS from message, just whatever iteration in our for loop that we're at. And so those are the only two required fields for this API, telling the consensus message submit transaction which topic it would like to publish this message to, and populating the contents of that message. So now we should be able to execute this, and again, we'll use our client connection to send this to the test network. After this message has gone to Hedera, we can get a receipt for it just like all other transactions on Hedera. So I will do that and log it to the console just so that we can make sure that all these consensus submit transactions are going through properly. Awesome. And so we're getting the receipt of each of these HCS messages and then logging it to the console. And so just like we did before, we should be able to pause now and test our implementation to make sure that we're both able to create a new topic as well as publish messages to that topic. So by going back into my terminal and running node index.js, we should again see a new topic created on the test network And then we should see 10 consecutive messages being published to this new topic. So you can see we're at consensus topic sequence number 6. Now we're at 7, 8, and 9. So that's awesome. We have now successfully published all 10 of our messages into this new consensus service topic, which confirms that this implementation of our code is also working properly. And so if you're building publish subscribe architectures or infrastructure, you would know that we're missing one final piece of this puzzle, which is the actual subscription. So ways that we can receive messages after they have reached consensus on Hedera that we can use in our applications, whether it's as an event message service or an event streaming service, an event queue, or any type of application that needs well-defined ordering. And so the way that we do this is by implementing the last two modules from our JavaScript SDK. The MirrorClient is a lot like our client here, but instead of connecting to the public Hedera test network, this MirrorClient will connect to a Hedera mirror node. And with that MirrorClient, we will subscribe to the specific topic that we would want with this mirror consensus topic query here. So let's do that now and make sure that we have the rest of our publish subscribe architecture working. So you're going to do this by running a new mirror consensus topic query. Actually, I forgot to establish our mirror client, so I will do that now. So const mirror, my mirror client. And so in this case, I'm going to use the available mirror node API from Hedera, but there are a variety of other services offering this, including Dragonglass and Kabuto to date. So this is hcs.testnet. And so now that we have our mirror client connected or pointing to the API that we would like to use, we can start building this mirror consensus topic query. So just like our other transactions here, there's a few parameters that we must define here. One of which is the topic ID. And so we set the topic ID to the topic ID that we just created. That way we're telling the mirror node what channel we would like to listen to. After telling it which channel or topic we would like to listen to, we can subscribe. And we'll subscribe using my mirror client. And then as part of that subscription, we should get messages back. And when we receive these messages, all that we're going to do is log them to the console. There's also a chance, though, that this subscription to the mirror topic results in an error, so we should also include some basic error handling here. In this case, we're just going to log the errors just like we would with the successful messages. Awesome, and I will clean this up a little bit to make it more readable. Let's break it into different lines here. And so this should be all that you need for your mirror consensus topic query. you can see that one of the required fields is the topic ID, and then from there you can subscribe using your MirrorClient connection. If we receive a successful message, we will print it out to the console. And similarly, if we receive an error, we will print that out to the console as well. So with this code, we should be able to do everything required in our publish-subscribe architecture. However, there might be one thing that we want to include, which is a way to sleep or delay our execution in between all of these processes. So I'm going to write a very basic sleep function here that you can use in your example as well. And so all this is going to do is pass in the amount of milliseconds that you would like to sleep for, and then it will set a timeout for that number of milliseconds and return a promise. So we might want to use this sleep function in between creating our consensus service topic and attempting to create a subscription to that topic in our mirror node. By waiting just a few seconds in between here, we're going to be able to have a stronger guarantee that our mirror node is aware of this new consensus service topic. In this example, I'll just sleep for maybe 5 seconds, but depending on how many transactions are going through the network and a variety of other factors, you may need to wait longer or shorter depending on what's going on. And so that should be everything that we need to build out this entire publish-subscribe architecture with this basic example. You'll create a new topic and subscribe to that topic from a mirror node. You'll publish 10 messages to that topic, and after Hedera has reached consensus and put them in a full order with cryptographic timestamps and running hashes associated with them, you'll be able to receive those messages from our subscription. So let's go back to our terminal and try to run this full example. I'm going to clear my terminal just so it looks a little cleaner, and I will run this again with node index.js. And so we should see our new topic created, and then it should wait 5 seconds before creating that consensus topic query. And you'll see that we have our 10 messages being published to this topic. And asynchronously, we will see the messages coming in from the Hedera mirror node. If you just give it a few more seconds, you'll be able to see all of the output here and all of the responses from this publish-subscribe architecture. Awesome. And so you can see here we have a lot of output. We have the new topic that was created. You can see when we send the messages 1, 2, 3, 4, and then you can see when we actually get these messages back from the mirror node here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So congratulations, this should be everything that it takes to get started building publish-subscribe applications on the new Hedera consensus service. Unlike traditional event streaming services or message queues, you have the cryptographic and decentralized infrastructure guarantees of the entire Hedera network. This is going to enable some radically new types of services and applications to be built.